All right, we got one section left. Welcome back, everybody. All right. Let's get down to it. We're gonna do examples. We're gonna find inflection points, concavity, and like the extrema, local max and local min. So previously, I gave you f of x equaled 1/3 x cubed minus 3x squared plus 8x minus 5. Our first derivative test showed us a local max at x equals 2 and a min at x equals 4. If we take the second derivative, we get 2x minus 6. So we're going to take 2x minus 6, set it equal to 0, and we solve, and we'll get x equals 3. From that, we're going to make a sign chart, and I'm choosing to use my previous values that I said, max and min at, as my test points here. So if I plug in positive 2, I got 2 times 2 is 4, minus 6 is negative 2. This is negative, which means it's concave down. Which would mean we have a max there, right? Looks like a max. And we stick in 4. 2 times 4 is 8, minus 6 is 2. 2 is positive. We've got a region of concave up. This does help us confirm what we saw earlier. We had a local max at x equals 2. We had a local min at x equals 4. Maybe I'll do this. You know what? Let's use a different color for that second one. And so it kind of confirms what we had above. We can see the max and we can see the min by using the concavity. So second derivative test is usually quicker to do than doing what we did above to find a local max and min. And I graphed this on Desmos. We'll take a look at doing more with graphing after we've done 4.6. But I found what f of 2 was, where our local max was. I said that was 5/3. We got it there. We had a local min at x equals 4, and that was at 1/3. Y is 1/3. And my inflection point was at x equals 3. We did this right here. Choose a different color for that. Let's do that one. But x equals 3, and that's right here. And you'll notice you can kind of see that it's doing some curving downward here. But when I get here, it looks like it's starting to curve up. Oh, curve up. It's kind of hard to eyeball that. It really is. It's kind of hard to eyeball that. Like, where exactly is that curvature, that concavity changing? So the second derivative will tell us, we set it equal to 0 to find those. That's called the inflection point. As a reminder, inflection point. Here it's concave down, and here it's concave up. And I'll make a little note on the side of what that is. CU is concave up. CD is concave down. Concavity is like an adjective. No, concavity is like a noun almost. It describes what the curvature is. Concave is like describing which way. I don't know. I don't know if it's I'm not an English major. Fuck it. Not even gonna try to be. All right, next example. Like we did before, we had 3 examples. We're gonna do the 3 examples here. Your next problem was negative x cubed plus 3/2 x squared plus 18x. We did that before. You found the first derivative before if you did it. So pause the video, work from it from here, and see what you get using this second derivative test. All right, I'll assume you did. Previously, we had negative 3x squared plus 3x plus 18 for the first derivative. Second derivative looks like negative 6x plus 3. So if I set that equal to 0, I get x equals 1/2. And we had critical values at -2 and +3, if you remember. So I'm going to use those as my test points. When I stick in -2, I get the graph is concave up, so it's doing that. And when I stick in +3, I get concave down, so it's doing that. Doing that is going to make this will be a minimum. That doesn't show up very well. And this one will be a max. And I know my curve doesn't line up here with the -2. I'm just showing the overall region. But if you actually pick the point, it shows like the bowl shapedness of it. And so it's pretty handy. And if we plot it, this is what it looks like in Desmos. So it's a little hard to see because this is such a narrow graph. Like -2 and -2 here and 3 here is not very wide, but look at those y values. Those y values are shitty. So this makes a very bad graph to graph. All right, we had one more example. I want you to try it. We had 5x to the 1/3 minus x to the 5/3. You already did the first derivative. I would recommend going back and using it. And I recommend not using the version where you found a common denominator. Okay? All right, I will assume you did it. We had that for our first derivative. When I take the second derivative, I have -10/9 times x to the -5/3 times -10/9 for x to the -1/3. And I rewrote this without negative exponents using radicals. And what I did here is I multiplied. We had x to the 1 over x to the 1/3. And I multiplied top and bottom. Let's do this a little bit better. We had 1 over x to the 1/3. And we want to get x to the 5/3 on bottom. So I got to multiply by something that gives me a 5/3. That's 4/3 down here, which means doing 4/3 up here, which is cube root of x to the 4th. So when I do that, I've got cube root of x to the 4th on top, and then a 1 from the first one, because that's still a 1. Oop. And then the bottom is cube root of x to the 5th. Don't dump the -10/9. We need that for concavity. So we've got the cube root of x to the 4th here. This is always positive. That's always positive. And the cube root of a positive number is always a positive. And if I add 1 to it, that just makes it more positive. So the top, ooh, what is that? Don't want that. The top is never negative. It's always positive. So we just need to look at really what's going on with the bottom. The top can never equal 0. So there's no like critical point or potential inflection point where the top is 0. There is a potential inflection point where the bottom equals 0, which happens at x equals 0. And if you'll remember, we had from first derivative, we had critical values at x equals 0 and plus or minus 1. So -1 and 1, we're going to test it. 0 is actually both a critical value and a potential inflection point. And when we did it before, we saw that I think it was showing increasing and increasing, but let's take a look at doing the second derivative test here. I'm going to use our local maxes and mins that we identified before. If I stick in -1, the top is always positive. The -10/9 is always negative. That's always negative. The positive is always positive, and the cube root, or -1 to the 5th power is -1. The cube root of it is -1. We've got two negatives. That overall region is positive. So we're doing concavity. It's concave up there. And when we do this one, we stick in 1. This is still the negative, but everything else is positive. We've got concave down. So this is doing like this, and this is doing like this. So this does confirm that we have a local min at x equals -1 and a local max at x equals +1. I know my curves don't line up with it, but they will on the graph. And we can see, like, for that the concavity to be going like that, we already saw from the first derivative that 0 was wonky there. Come down and take a look at the graph. And we saw the graph before, but now I've plotted my 3 points. And we can see that we are concave up right here. We are concave down right here. And we have no concavity here. And our derivative was a problem here. That's where we said we have a tangent line, vertical tangent line. Okay? We'll tie all this together after we've done a little bit more with 4.6 coming up. But that's it for these videos. I hope you enjoy 4.5. I'll get them up on Canvas when I can. I'm going to link them in Discord. Peace.